Hey, what's up, guys? Welcome to Roman Reactions. We're gonna be going over some Organic 2 final review. This video is like a test run, so still pause the video, see if you can do the problems, and let's go. So this first one, predict the products of the reaction. So we are doing addition of HBr to a double bond with a peroxide. So whenever you see a peroxide here, you know that it's going to be a radical initiator. So RO is going to split into a radical, and it's actually going to cleave the bond between H and Br. So what's going to form is you're going to have ROH form, so an alcohol, plus a bromine radical, because he inherits one of these electrons. So this bromine radical is going to attack the double bond, and he is going to attack it so that it forms the more stable radical. So he's going to attack here, and again, this is, you got to draw actually half arrows for each side. So here, let me do that right. Let's draw a half arrow here and a half arrow here, and then this other electron in this bond is going to be going up there into the tertiary radical. So product's going to look like this with a radical, a tertiary radical, and then that is going to break this bond between the hydrogen and the alcohol, and we're going to finish the addition. So overall, we added an H and a Br across the double bond, and of course this could be a stereocenter, so we could actually have two enantiomers form here. One thing to know is that since we had the peroxide, this went anti-Markovnikov addition. If we just had HBr added across this double bond, what we would have gotten would just be Markovnikov addition, where the H adds to the less substituted carbon. So it's important to keep in mind when we're going Markovnikov and when we're going anti-Markovnikov. So let's look at this next one. We've got another alkene. This time we're adding NBS, so N-bromosuccinimide. Now, this is actually going to be a big flag for allylic bromination. So the double bond is retained here, but we're actually going to have radical addition of bromine in the allylic carbon, meaning the carbon that's next to the double bond. So NBS, what makes it different is it supplies only like a little bit of bromine at a time. So we actually, instead of attacking at the double bond, we attack at the allylic position. All right, let's try this one. So this one, we don't have a radical initiator. So this is just going to be normal ionic addition. So it's when we add HBr, the double bond is going to attack at the hydrogen, and we're going to have ionic intermediates, meaning we'll have the hydrogen add here, and we're going to have a carbocation here, and we're also going to form Br minus. So why did we put the carbocation here and not, I don't know, here, here, or here? Well, we choose to put it in the spot that would be the most substituted. So that is why we're going to put it in the tertiary carbocation spot. Now, one thing to notice, though, is that we are at 80 degrees Celsius. And that's important because this intermediate actually has two resonance forms. So I'm going to draw the second one out. So in the second resonance form, we're going to have this double bond flip over here and a carbocation there. So that means that this bromide ion could actually attack at either position. He could attack at this carbocation or this one. So which one is he going to attack at? Well, since we are at high temperatures, we are going to form the most thermodynamically stable product. So if we imagine a diagram, a reaction diagram for this, we can form two products from here. So when we react our reactant with hydrobromic acid, we can either form this product, which has the bromine added to our first carbocation, and this product, which has it added to this carbocation. So if you notice, this resonance form right here applies to this, and this applies to that. So the idea is we have two routes we could go in this energy diagram. So we can either go on the kinetic side, so we can go on like, it takes less energy to get here, or we can go on the thermodynamic side, where we take a little bit more energy, but we actually come out with a more stable product. So when we're at higher temperatures, we're going to tend to go with the more thermodynamically stable product, even if it takes a higher activation energy to do so. So in this case, at high temperatures, we are going to form the thermodynamic product, which is going to be through this resonance form. So the bromine is going to attack on this carbocation, and we are going to form here. Now, I haven't really explained why this is more stable. The reason is because of this double bond. This double bond right here is a tri-substitute double bond. It's got a carbon here, and carbon here attached to it. So if we formed this product up top, let me make some room. So if we formed this product, which would be our kinetic product, not our thermodynamic product, we would only have a di-substituted double bond, so not as stable. But why is this one more kinetically favorable? Well, the reason of that is because after this first step, where we had the hydrogen add, so this hydrogen added here while this double bond formed. This bromine atom that just broke off of this hydrogen is going to be closest to this carbocation. So he's going to want to just naturally attack here. This is called the proximity effect. It takes a little bit more energy for him to move over here and attack at this spot. So when we're at high temperatures, he's going to tend to attack over here. When we're at low temperatures, he's just gonna be chill attacking over here. All right, draw the products for this reaction. So now, I alluded to this, we're at low temperatures. So again, the first step is the same. We're going to add our hydrogen, and since this is ionic, we're adding it onto the least substituted carbon. So I added the hydrogen over here. So this double bond is going to attack here, breaking this bond. And if you remember, we had the bond broken between the bromine and the hydrogen, and we have a carbocation form here. So since we're at low temperatures, he's just going to slide right in here, and he's going to be pretty comfortable forming this product. It's not as thermodynamically favorable as the other possible product, which has this resonance form and would be this product. It's not as thermodynamically favorable, but it's more kinetically favorable. So we call this one the kinetic product, and this one the thermodynamic product. And again, at low temperatures, I'm not going to get the thermodynamic product as our major product, just the kinetic. All right, let's look at this one. So whenever we have a diene reacting with, and I drew this wrong, but this is supposed to be a what we call a dienophile, meaning an alkene. Whenever we have these two reacting, we're going to go through what's called the Diels-Alder reaction. So in the Diels-Alder reaction, we're going to form bonds between the diene and the dienophile. So how do we form these bonds? Well, one of them comes from the diene, the other comes from electrons from the dienophile. And then by these electrons coming down here, it pushes these ones over here. So our product, now we can also talk about the stereochemistry of our product, because if you notice, this this dienophile right here is cis. So its groups are cis to each other, meaning that they're going to have to be cis on the product. But the question is if these groups are going to be cis or trans to this methyl group. So in order to figure that out, we're going to have to draw the chair configurations. So this is a cyclohexane with one group away, it's got the methyl. So I'm going to draw that down here. And the other group away, it's got the ester group right here. And they have to be cis to each other, so I'm going to draw them like this. And again, these chair forms, they have I shouldn't draw them in resonance. They have two interconverting structures in which the chair flips up. So I'm going to draw going to draw each structure for this. So when the chair flips up, this carbon becomes this one, and this ester group actually moves from the axial position into the equatorial position. So we'll draw that. This one over here becomes this carbon, and this ester is going to move from the equatorial position into the axial position. And then over here, this goes into the equatorial position. Now the question is this chair configuration more stable, or would the alternative chair configuration be more stable? So yeah, I know there's a lot of drawing, and I'm realizing that now. But the alternative chair configuration would be in which these groups are trans to one another. So if you notice in this one, I'm just going to write cis, because I wrote all these constituents cis to each other. Right here, this methyl group is cis, meaning that it's on the same side of the plane as these groups. Same with on here. This is actually, it's important to note that this methyl group is actually facing down, even though I kind of drew it like it's coming out to the side. It's really, it's facing down, just to make that more clear. So the alternative way to draw it would be to draw them trans from one another. So I'll draw that quickly. We're going to have the methyl in the axial position. So we just have to figure out which of these two, the cis or the trans forms, would be more stable. And really, because in the trans configuration, you can see that we have two equatorial positions next to each other. So there's going to be a little steric hindrance there. And these groups aren't going to really want to be interacting in that way. But if you notice here, we have it axial and equatorial, and equatorial and axial next to each other. So really, what ends up being more stable is this cis conformation. So the way we might want to draw this as our product is we could draw with these wedges here, and that would, make it clear that these are going to be cis to one another. All right, predict the products of this reaction. So in this one, we've got a ketone reacting with a Grignard reagent. So if you remember, with any ketones, I'm just going to draw a general run, or aldehydes, they have one characteristic reaction, and that is nucleophilic addition. So that is when a nucleophile comes in and attacks at this partially positive carbon. So he's going to attack here and push these electrons up to the oxygen. Again, he could also attack at an aldehyde, do the same thing. But ultimately, what's going to form is this. So I'm drawing the ketone forming this intermediate, which usually is protonated, and our final product is usually an alcohol. So this is the characteristic reaction of aldehydes and ketones. So let's apply this to the Grignard reagent, who is a nucleophile. And the reason why he's a nucleophile is because in this organometallic bond between the C and magnesium, it's actually going to be, if I drew it out, it's actually going to be a very polar bond, meaning that the magnesium is really positive and most of the electrons at the carbon. So what's important about that is because since it's a polar bond, we can create a carbon-carbon bond because the carbon is very electrophilic. So we can have a partial negative on the carbon, partial positive on the magnesium. And what will result from this is basically a carbon nucleophilic attack. So looking a little like this. So after we do our acid workup step with water, going to have protonation here, and our final product will be this alcohol. Now let's look at when we do nucleophilic acyl substitution. So if you remember, with any carboxylic acid derivative, so that could be an ester, it could be a acid chloride, it could be an amide, it could be an anhydride, or it could just be a carboxylic acid. But no matter which one it is, it has one characteristic reaction. That's when you react it with a nucleophile. The first step is the same, where you have this intermediate, but instead of doing nucleophilic addition, it's going to be substitution. So what happens is the electrons from the oxygen actually push back down and push out the leaving group, and the leaving group being this alkoxy group, the OCH3. So now your product is going to be a substitution product because you substituted the OCH3 for the nucleophile. And then, of course, you also have this floating around in your solution. So if we apply that to this reduction reaction using diol H, in this case, the hydrogen is actually acting as a hydride nucleophile, and he's going to do nucleophilic attack here. And it's the same thing. We're going to have this intermediate, OCH3, and I'm going to draw the hydrogen in too. And then the oxygen comes back down, or pushes his electrons down and kicks off the leaving group. So what we form is this. So we reduced a ester into an aldehyde. Now the question is, can we reduce any more? So is diol H a strong enough reducer to reduce an aldehyde? And the question is, or the answer to the question is no. If we instead had something like lithium aluminum hydride, well then this is actually a strong enough reducer, and we would do nucleophilic addition now, and our final product would be an alcohol. So it's important to keep in mind, is my reducing agent strong enough to bring me all the way to the alcohol, or do I stop at the aldehyde or ketone? So that's always an important question to ask whenever you're doing that. All right, this next reaction is going to be a little bit different because even though we have a ketone here, he's not going to do nucleophilic acyl addition. So in this case, we have what's called an alpha-beta unsaturated ketone. Alpha-beta meaning at the alpha and the beta carbon, and unsaturated meaning that there's a double bond there. So what this means whenever we have an alpha-beta unsaturated ketone is that we've got a couple resonance forms, because we know that we can push up these electrons up into the oxygen. But we can also push the electrons from the double bond over here too. So whenever we have this, we really have, and this is positive and this is positive, we really have two electrophilic sites. So we have this carbocation right here, and we have this one right here. So whenever we're doing attack, we have to ask ourselves, is it going to attack at the carbonyl carbon, which would be right here, or is it going to attack at the beta carbon? Because both are electrophilic. Now, how do we distinguish between these two regions? So on the carbonyl carbon, it's what it would be called a hard electrophile, meaning that the positive charge is pretty concentrated around the carbonyl. But with beta carbon, he's what we call a soft electrophile, meaning that his positive charge is relatively dispersed through the molecule. So if we have a soft nucleophile, like this organocuprate reagent, then we're actually going to attack at the beta carbon and not the carbonyl. So our addition product is going to look like this. And the second step should be with water, by the way. Now, let's imagine if we attacked with, let's say, a Grignard reagent. Well, in this case, a Grignard reagent has a really concentrated negative charge. So it's what we call a hard nucleophile. So he's actually going to attack at the carbonyl carbon. And our product will be addition across the carbon-oxygen bond. So we're going to have a product that looks like this. All right, so now we're going to be reacting excess Grignard reagent with an ester. So how is this going to work? Well, the first step is where this bond between the CH3 and the Mg, magnesium, is going to break, and we're going to attack at the carbonyl carbon. And if you remember, like we just did, the end product will be nucleophilic substitution. So we'll have this ketone formed, but we'll also have OCH3 formed. But since we're reacting excess Grignard reagent, really, we can react again. Because anytime you do nucleophilic acyl substitution, you should ask yourself, is my nucleophile strong enough to keep attacking? And in this case, yes, it is. So we'll attack again. And our final product is actually going to, after we protonate it with water, is going to look like this. It's going to be an alcohol. All right, predict the products of this reaction. We are reacting a stilbene derivative with hydrobromic acid. So it's going to be addition, but the question is, on which side is the bromine going to add? So with this electrophilic addition, it's got an ionic intermediate because there's no radical initiator. So the double bond is going to attack at the hydrogen and is going to form a carbocation intermediate. So our question should be, which carbon is going to bear the positive charge? And that will tell us which one the bromine is going to attach to. So before I draw the double bond in, or the positive charge, I'm going to draw out how this might look. So let's say we put the positive charge here. All right, well, we just put the positive charge next to this benzene ring, who has a nitrile group attached to it. So nitrile group has a dipole that looks like this. So this carbon is pretty partially positive. So what he's going to be, lacking electrons. So he's going to want to pull electrons out of the ring. So he's going to be what's called a electron withdrawing group. If we look at instead putting the positive charge on this carbon, well, because of these lone pairs, the OCH3 group can actually donate resonance forms into the benzene ring. So because he can donate resonance forms into the benzene ring, he's what's called an electron donator. So he actually donates electrons into the ring. So the main way to distinguish electron withdrawers from electron donators is, well, one, do they have lone pairs of electrons to donate into? Because if they have lone pairs, then they're definitely donators. Like, for instance, if we have this group attached to a benzene ring, well, the amide nitrogen has electron pair, so he can donate those into the ring. Now, he's not going to be the strongest donator, but he's still going to be a donator. So that's the biggest thing to look into. The other thing would be inductive effects. So, for instance, if I had a benzene ring with a carbon attached to it, so a CH3 group, well, CH3 groups are electron donators by induction, not by resonance. So he's going to be donating into the ring even though he doesn't have lone pairs. Now, if we're looking at electron withdrawers, the main thing we want to look at is if that group has a partial positive charge. So for instance, let's look at maybe this group. So if we have an acyl group attached, then we have a partial positive on this carbon, and partial negative on this oxygen. So because of his dipole, he's going to be pulling electrons out of the ring. So the partial positive charge is going to want to be closer to the ring that has electron donation. That way it stabilizes the positive charge. So this positive charge is going to be right here. And that means that the hydrogen added on this side, which means that the bromine is going to add on this side. So that would be your final product. All right, so this is going back to similar things, but this time doing it with electrophilic aromatic substitution. So we are doing nitration. So the first step of any electrophilic aromatic substitution reaction is the formation of an electrophile. So HNO3 is going to look like this, and H2SO4 is going to be a strong acid who's going to donate his proton. So we're going to form this intermediate, which looks like this, H2, having a positive charge on both the nitrogen and the oxygen. And the oxygen is going to act as a leaving group And the electrophile that we form, oh, and these electrons push down. The electrophile we form has a positive charge on the nitrogen. So this electrophile could attack at a couple different areas of the benzene ring. So let's say, for instance, he attacks right here at the meta position. And he's actually not the one doing the attacking. I should make that more clear. He's actually being attacked by the benzene ring. So what we would form then is this nitro group on the benzene, who is a strong electron withdrawer. So in this intermediate that's formed, we have a positive charge here, and he's going to be withdrawing electrons. In this case, the positive charge can take up a couple locations on the benzene ring, like that, or it could be, I'm running out of space here, but you know, it just continues, or it could be here. So the idea is this positive charge isn't ever touching this carbon, the carbon that holds the amide group, who is, as we said earlier, an electron donator, because he has that lone pair and can donate into the ring. So this intermediate wouldn't really be very stable because the positive charge doesn't have any stabilization at the meta position. So really, we're not going to do attack from the meta position. But let's imagine that we put it ortho. So right here. The structures would have a positive charge here. The other would have it here. One resonance structure would provide stabilization because he would put the positive charge right here on the amide group. And the reason this stabilizes is because this amide group is able to then donate in. And because we have this resonance structure right here that has that stabilization on the carbocation, the ortho position is going to be a favorable position for attack. But in this case, what might be an even more favorable position would be the para position, because it has the same benefits as the ortho position in the fact that it's got the partial positive charge on the amide group during one of the resonance forms. But because the amide group is pretty bulky, he's not going to want a nitro group right next to him in the ortho position. So really, this is going to be the major product, is when the nitro group is para to the amide group. So whenever you're doing these problems, you don't want to be looking at them every single time going through all the resonance structures. I just did that to demonstrate how the partial positive charge is distributed. Instead, you want to just look at whatever the group is that's directing. In this case, it is the amide group. Since you know that the amide group is an electron donator, electron donators are what we call ortho para directors. Electron withdrawers are going to be meta directors. For the opposite reason, because we don't want the positive charge to be localized near them because they're withdrawing electrons and they're going to destabilize it. The exception to this rule would be whenever we have an alkyl halide or a benzyl halide, aryl halide, whatever. Because, yeah, these guys are electron withdrawers, but really, since they have these lone pairs, whenever there's a positive charge near them, they can actually donate a little bit into the ring. So they're kind of like on the fence between being donators and withdrawers. But since they can act as donators, we also call them orthopara directors. So the way I like to think of it is anything that's got a lone pair is an orthopara director. Also, alkyl groups are orthopara directors. Everything else that's got a partial positive, that is going to be a meta director. All right, this reaction is going to be a condensation reaction. And the way we can identify that is because we have two carbonyl groups, and one of them has alpha hydrogens, so he can readily form an enolate. So we're reacting it with strong base, so this base is going to pull off the alpha hydrogen. Now, it really wasn't hard to figure out which alpha hydrogen to take from, because there's only one in this reaction. Now, once we form an enolate, we're going to do the reaction, the only reaction that ketones and aldehydes do, which is nucleophilic addition. So now, with this nucleophilic addition, the enolate acts as the nucleophile. So he's going to attack at the carbonyl carbon, and our product, draw it over here, is going to be, after the nucleophilic addition and after the protonation step, we're going to form an alcohol next to a ketone. So this is called an Aldol condensation. And the way it gets its name is ald for aldehyde and ol for alcohol. So aldehyde because, well, a lot of times it takes aldehydes and it forms sometimes aldehydes. Not in this case, but it could. And then ol because it forms an alcohol. But the reason why it's called an Aldol condensation is because whenever we have this alcohol group or this hydroxyl group near a benzene ring and also near a carbonyl carbon, we've got the potential for a lot of conjugation, meaning a lot of double bonds that are lined up near each other. So this hydroxy group, even though it's usually a bad leaving group, in this case, it's actually a pretty good one. So again, we have a strong base in solution. So this reaction, the condensation part of the reaction, goes through what's called an E1CB mechanism. For the E1CB mechanism, it starts with the removal of this hydrogen. And since it's E1, it goes to an intermediate, like this. And then these electrons are going to kick off the hydroxy leaving group. And we're going to form a product like this. So again, why did we form this condensation product? It really has to come down to how stable the end product is. Now, since we have so many double bonds near each other, and this molecule is going to be mostly planar, the electrons are all going to be in conjugation with each other. So it's going to make a pretty stable system. Another reason why this forms is because, and I really should have been drawing this the whole time, but these reaction arrows are actually in equilibrium with each other. So, oh no. So I really should have been drawing equilibrium arrows this whole time. And really, with most of our carbonyl reactions, they're in equilibrium. But the thing is once you kick off the hydroxyl group, it is not in equilibrium. It's a forward reaction. So if you remember Le Chatelier's principle, it tells us that if I am reducing the concentration of this product, so this one right here, it's going to drive equilibrium forward, which is going to drive this entire reaction forward. The reason why I'm lowering the concentration of this is because it's all being converted into our final product. So really, the reason why we do this condensation is because it drives the equilibrium forward. Now, if you notice though, our final product in this is not really a final product. That's not right. It looked like this. Why isn't it a final product? Because we can still form an enolate. We still have the base in solution. So we can pull off another alpha hydrogen and form another enolate. And this enolate will just attack another. I'm going to draw these in equilibrium, Even though you really don't have to because it ends with the condensation step, it's still, nice to draw them in equilibrium. So he's going to attack at another molecule of himself. So it's going to be like that. And our final product well, before the condensation, will look like this, because we've essentially combined two of these molecules together. And, you know, just so I can save myself drawing this like for the 50th time, I'm just going to draw the condensation product right here. So that's after the hydroxy group leaves. Same mechanism as before. All right. So now we are going to have base in solution again, except this time we've got an ester. So it's not going to go by the nucleophilic addition route that we did before. It's actually going to go through substitution. So first step is the same though. Because there's an acidic proton here, anytime we have a base, we want to identify our acidic proton. So we form the enolate in our first step. And really with these condensation reactions, the only thing that makes them any more difficult than, say, like the nucleophilic addition or nucleophilic substitution is just that formation of the enolate step. Because all the other steps after that are really just nucleophilic addition or nucleophilic substitution. In this case, it's going to be substitution because we have the OCH3 group, which can act as a leaving group. But I'll draw the intermediate that has all the groups together, just to show this. So whenever you're combining two of these molecules, sometimes it can get confusing. So I'm just going to draw both of them like this, and then just connect them like here. So that's going to be our new bond. And then after these electrons come down, it pushes off the leaving group. And our product is going to look like this. So sometimes it's hard to see like how you drew it, because you have to like kind of redraw it. But that's what our product's going to look like. And we don't really have to use the equilibrium arrows because we had that leaving group leave, and it really drives the reaction forward to our final product. And this is called the Claisen condensation. So last time we did the Aldol, but this one is Claisen. All right, last one. So whenever we see a alpha beta unsaturated ketone reacting with an enolate, because we know that this is an acidic proton, it's going to form an enolate. After this forms an enolate, we have to wonder, is it going to attack at the carbonyl carbon right here or at the beta carbon? Remember what we talked about earlier, soft versus hard nucleophiles. So when we have this enolate with all this conjugation, this negative charge is going to be really nice and dispersed. So he's going to be, you know, just out there relaxing in all his conjugation. He's going to be a soft nucleophile. So he's going to want to attack at the soft electrophilic region. And if you remember, the beta carbon is the softer region. So this mechanism is going to go through attack at the beta carbon. And again, I'm going to first start by drawing each of my products separate and then by connecting them. So here, this is, it's a little sloppy, but you know, this is its own carbon right here. So let's not miss that carbon when we redraw this. Another thing is there's a negative charge here. So when we do our acid workup step, he's going to be protonated. So our final product, let's see, this is 1, 2, 3, 4. 1, 2, 3, 4. It's always really helpful to count the carbons. That way you don't miss any, because that's always my biggest problem, is like missing the carbons. But I'm pretty sure that I got them all there. So this is going to be what's called the Michaell addition. And that is the last reaction that we're going to do. So that was kind of, took a lot longer than I thought it would. But I hope that was a good, you know, sample size of reactions to go over. I might do some more. I really got to go back, watch the video, see how it went. But anyway, hope that was helpful. See you guys.